Thank you very much for having me. It's very nice to be here, even though it is virtual, and it's a little bit unusual way to give a talk. I've never given a talk virtually before, as probably most of the attendees similarly have not given virtual talks before. I mean, most of the presenters are. So, as mentioned, my talk today is about using predictive analytics and machine learning to support critical decisions and to reduce risk. I'll talk a little bit generally about that, but specifically giving examples from my work at NASA, and then my work as co-founder and chief technical officer of the company that I founded, Synolytic. So the first question is, why at a machine learning conference do we want to discuss risk and decisions, critical decisions and risk management? And the reason is that we don't want, as my colleagues at NASA used to say, to have a bad day. So for most of us at work, especially if we work in sort of customer-facing business positions, a bad day at work does not include disasters or catastrophes. It's generally something much less serious than that. So the question is, what's the relationship between NASA, Hollywood, and machine learning? And what I'll be talking about today is something that I think is fundamental to many who practice machine learning, and for probably also many who use the products of machine learning, the analytic products in decision making. Most of what we do in non-scientific applications of machine learning, one way or the other, helps to support decisions, whether those decisions are taken by a human who takes an action, or whether they're taken automatically by a machine, for example, in serving up different ads depending on user behavior, or different movie recommendations depending on what you've been watching in the past on your streaming platform. When we use machine learning, when we develop algorithms and apply machine learning algorithms to specific problems, we always are baking in assumptions to our models, to the applications of models, et cetera. Some of those are conscious assumptions, some are unconscious. And so since many of the applications of machine learning are used to support decision making, some small decisions, some large decisions, it's important for us to understand what risk is and how we can apply that better in decision making. So I will, in this presentation, discuss what critical decisions are. I'll briefly discuss risk and uncertainty, and then I'll go through those aspects fairly quickly. I'll then discuss applications of predictive analytics to assess spacecraft risk at NASA based on my experience, and then applications of machine learning to assess financial risk for movies in Hollywood, and leave you with some conclusions that I hope you can take away and that will help you in your work or your research when you're considering decisions, decision making, and risk. So firstly, what are critical decisions? They're different than our normal everyday decisions in the sense that they're those decisions which impact things of high value to a person or to an organization. So as an example, an airline pilot, when they have the go, no-go decision to take off or to land, That's obviously those are obviously critical decisions, because if they make the wrong decision, they're putting at risk the lives of the passengers and crew on board the plane, people on the ground, et cetera, as well as the airplane itself. Doctor deciding on a course of treatment is making critical decisions. If they make the wrong decision, they may adversely affect the health of their patient. A venture capital firm deciding to invest in a new company, or a business investing in new products or services is making critical decisions. The thing at risk there is the investment. So when we make decisions in a sort of everyday way, we typically just weigh cost versus benefit. Now, most of this can be unconscious or intuitive, gut-based decision-making. And the process we use is that we take in all available information, which is relevant, or which we feel is relevant. We use that information to inform our choices given our resources, our goals, and our constraints. So as an example, if this is again just a kind of everyday example, if I'm outside of my house and I'm somewhat far from home and I notice dark clouds are approaching, indicating rain, I check the weather forecast on my phone and I notice that there's a 50% chance of rain. So I then have to make a decision. Do I spend, say, 10 euros on a taxi, a few euros for the metro, or do I walk home? And I balance the risk of getting wet with the cost here of taxi versus a metro ride, which is much cheaper, or walking, which is free, but in which case there's probably a higher likelihood of getting wet. So that's a very simple, example, which is not a critical decision, because there's not much being risked here other than maybe getting wet. Critical decisions use the same process, but the difference is that they have a much heavier, normally you use a much heavier weighting of risk in the equation. So here's an example of a good example of a critical decision being informed by a lot of information upon which numerous smaller decisions are being made. Here, the pilot is looking at their landing checklist, they're checking instruments, they're seeing that all is looking green, so the speed brakes is armed, landing gear is all down, flaps are in the right position, etc. If any one of these items on this checklist were not positive, then there is a decision path the pilot has to make, which is going to inform that critical decision whether to land or to do something else. For example, if the landing gear doesn't come down, it's a very, very serious situation. The pilot has to then inform the control tower, and they have to issue an emergency, do probably circle the airport for a while to burn off fuel, let emergency crews prepare the runway, etc. So some critical decisions are, as in the case of a pilot, very time sensitive. That is to say that the pilot has to make decisions in a matter of seconds as to whether to proceed with landing or not. On the other hand, some critical decisions are much more deliberative. For example, if you're building a new building and you're going to spend 30, 50 million euros on it, that is quite a deliberative process. if you're building a new power plant, for example. Also, very deliberative process. You have time to work through the various decisions that will lead to the final go, no-go decision. So in complex systems, critical decisions are typically, that can take time, a lot of time, can take many years, in fact. And this image here that we're looking at, the flow, is from the Department of Energy. It describes the typical acquisition management process for when they're deciding to build, when they're deciding on a new project. And so, as you can see, there are many approval steps, a lot of weighting of the decisions need to be made. Now, poorly informed decisions often, of course, lead to bad outcomes. And in making decisions, we need to, in making critical decisions, we need to get as much information as we can to understand the risks and to understand the uncertainty inherent when we estimate the risks. So that leads us to ask then, what is risk? And risk, simply stated, is a possibility of something bad happening. To be a little bit more specific, we can discuss the mathematical expression of risk, which is the probability of an event multiplied by the consequence. This is, in this case, it's the adverse consequence. And this understanding of risk is typically used in a utility with a utility function, where you're balancing your understanding of a few different outcomes, sometimes many different outcomes, against the likelihood of each outcome. And you come up with a utility function that you try and maximize, or a maybe risk function that you try and minimize. And essential to this, to understanding uncertainty, to understanding risk, is measurement of uncertainty and understanding uncertainty. Uncertainty is typically expressed as a lack of knowledge or lack of certainty about something we're concerned with. And it's broken out into two different types: epistemic uncertainty, which is a lack of knowledge, and aleatory uncertainty, which is the inherent randomness of phenomena or situations. And these are, of course, expressed by probability distributions. I'm showing simple Gaussian distribution here, but very often, especially when it comes to measuring risk, we have non-symmetric distributions. Highly skewed distributions are pretty typical. So now let me explain and go through a little bit of how I used applications of predictive analytics to assess spacecraft risk while I was at NASA. So I started at NASA, working at NASA a couple of months after the Columbia disaster. The first slide I showed earlier in the presentation of the Columbia disaster in 2003, that was 1st of February. Around the 1st of May of that year, I started working at NASA specifically to assess the safety and reliability and risk of new spacecraft and launch vehicle concepts that were being reviewed and looked at as part of plans to replace the space shuttle. Now, this was underway prior to the Columbia disaster, but it was accelerated with that disaster. NASA realized that they needed to replace the shuttle program, and they needed to do it as quickly as possible. And they elevated the assessment of risk to a really primary place where perhaps it hadn't been during the shuttle program. Now, the problem was at the time that the way of estimating risk, of assessing it, used these very static, slow models. It was risk is assessed probabilistically with these complex systems, and the models were often developed in Excel, as you see on this screenshot of a tool, or in custom software that frankly was very cumbersome, not very useful, was very slow to develop models in, and was quite prone to errors. So what we faced was a situation where we wanted to change this, and the question was, how can we take all of this very, very complex information about launch vehicle and spacecraft design and put it in a framework so that we can analyze many, many concepts quickly. So our solution at my team was to build a software, analytic software that performed this kind of tree-based probabilistic risk assessment very rapidly using predictive analytics instead of this manual kind of ad hoc and bespoke way of assessing the risk of the systems. And this had the advantage of solving many of the problems of the legacy approach, which was, started in the 90s and had carried on into the early 2000s. So how do we apply this? Well, we worked on this very, very intensively, 14, 16-hour days for a few years. And we used a software, fortunately, it was ready when in 2005, NASA decided to begin a program called ESAS, which was to assess a large number of configurations of launch vehicles and spacecraft, which we led the assessment of those. And that led to the development of the Ares program and the Constellation program, and led to the construction and launch of the Ares 1X. During the about 90 days, roughly 3 months, 4 months, that we took part in the initial phase of that study, we were able to run about 100 or more configurations, whereas another team that was using the legacy approach only was able to analyze 2. So that was a pretty substantial increase in effectiveness on our part. The one important thing that we also did during the development of our software and in the application of the predictive analytics that we used was that we established that it was essential to have a good understanding of uncertainty in our risk assessments. Point estimates are definitely not adequate when you're speaking about billions, or in the case of a 30-year program, like what we were assessing, hundreds of billions of dollars, things of national consequence, of historic nature and value. So what we wanted to ensure was that we were able to have a good understanding of not only the point estimates of the risk, but also the uncertainty. And one of the things that we realized as we developed this was that it's essential to declutter the decision space. You'll see here that we have 7 concepts side by side, rather than, as I mentioned, we ran more than 100 during this period. But it was essential for for the people that were using the analysis to be able to compare things side by side. So it's very important that the decision products and the decision space compares things that are comparable, and that they are able to understand the uncertainty involved, because a point estimate by itself with these kind of decisions is not adequate. So this led in the end to the green light of, as I mentioned, the Ares program, constellation, and then eventually the Space Launch System, this is a computer-generated image of. Space Launch System is being built right now and will be used by NASA to usher in the next, to replace the space shuttle, but also to usher in the next generation of the United States in space, hopefully to take astronauts to the moon within the next 5-6 years, and then potentially even to Mars in another 15 or 20 years. So after while working at NASA, I got interested in something which seems quite unrelated probably, which is risk assessment or financial predictions of how films would do in Hollywood. Essentially Moneyball for the film industry. And if any of you have seen Moneyball, you know that it's a film about the application of predictive analytics to baseball, and enabled a team. I mean, it's a real story. Enabled the Oakland Athletics to end up, I think, winning, or at least doing very, very well in the Major League Baseball, the year that it was instituted. So when I was living in New York when I was working at NASA, and as such, I met a lot of people from the film industry. And I ended up, as a side project, working with the film producer who's interested in raising a film fund. And he wanted me to do Monte Carlo analysis, which I did. And the reason was that his investors were very worried about putting in large amounts of money. In this case, it was tens of millions of dollars into a film fund to finance films. The reason being that films are a highly risky enterprise to invest in. It's essentially like a venture capital exercise where only about 30% of films are profitable. Here, I only show you these red numbers are how much each of these films lost, is estimated to have lost. These are high-profile films, big studio tentpole films. And with each of these, there are many, many, many other films each year that lose money from mid-sized to small-sized independent films. So the question was, how do we do this in a better way? And what I decided to see if it would work was to apply the same type of predictive analytics, the same type of systematic risk assessment methodology that I was using at NASA to the film industry. And so what we did is to build a company called Synolytic, which does exactly that in almost it's software platform for the film industry. And what we're doing is to replace the current way of functioning, which is very similar to what I experienced at NASA, where people built ad hoc models. They used data from all different sources. Nothing was configuration controlled, et cetera. And so in doing that, a couple of steps, I of course can't describe the whole system, but just a couple of key aspects of it is that we value talent algorithmically. So we look at how actors, directors, producers, writers, et cetera, have performed, how their previous films have performed. We use a bunch of different weightings, and we can calculate algorithmically how a kind of ranking or a score by country, genre, by revenue stream. And what this does, it allows our users, those film studios, to rapidly compare talent and understand better the value potential they have in their films, and thereby the risk that they're assuming in using, say, one actor over another. It's also used in our predictive revenue forecasts of films. And so what this helps us to do, along with our machine learning that we use to predict revenues from films, is it allows us to reduce the financial risk through using various machine learning algorithms. And what our system does is to predict the financial performance of films. We flow these forecasts directly to sophisticated financial tools, which enables the user to understand if their film will break even, what the likelihood of profit is, what the likelihood of loss is. And all the analyses are standardized so that the stakeholders will see the same information. Another thing that we have done to make this very explicit, and this is based on what we did at NASA, was to encode the uncertainty and make it very, very explicit for both for the analysts and for the users of the analytic products, the managers, the studio heads, the people that are making the green light decisions. So we, as you see in this screenshot, this is a screen capture of our predictive model, which has output domestic and international forecasts for a film that we were running. It expresses confidence levels for each of those forecasts across various revenue streams. And the user can choose a different confidence level depending on their risk appetite. So if the other information that they have about the film tells them, well, it might be a little bit risky, then they'll choose a high confidence level, meaning that they want high confidence that the film will make at least X number of dollars, so that they have a higher chance of breaking even and making a return on their investment. And this also means that everybody, all of the stakeholders are on the same page in their understanding of what the risk is and what the confidence in their decisions are. So in closing, the conclusions and kind of what I would like to express to all of you in terms of machine learning and AI in any of the applications where you are informing decisions or where there's risk involved, especially critical risks, whether it's monetary loss of property or potentially even loss of life, that the important takeaways are to use scenarios and even scenarios of scenarios. So point estimates are not adequate at all. What you want is a very large decision space. From that very large decision space, you want to reduce it, because us being the humans, we don't do very well when presented with a lot of decision choices. You want to be as explicit as possible about the uncertainty involved, so that as an analyst, you want to make sure that you calculate uncertainty well. As a user of the product, you want to make sure that you understand what the uncertainties involved in your decision are. You want to make sure that the decision products or the choices are comparing like quantities. And in the end, you want to make clear to the risk acceptor, the person who's making the decision, what the risk and the uncertainty are, that they're assuming. And with that, I end, and thank you very much for your time.